Math, it's all about math, the wonderful world of math. Welcome to the wonderful world of math. Here we're going to do some trigonometry. Today we're going to pick up where we left off with the half-angle identities. We're going to start with sine and cosine half-angle identities. So previously we have established these two identities, and all we want to do today is do examples of how to use them. So I'm going to say something like evaluate cosine of pi over 8, or find the exact value for cosine of pi of 8. And you'll realize that this is not one of the angles that we do a lot, right? We know pi over 4 and pi over 3 and pi over 6 and all the quadrantal angles, but pi over 8 is not one we have a lot of experience with. But understanding that these half-angle formulas allow us to find the sine or cosine of half of a well-known angle, we can ask ourselves, is pi over 8 half of a well-known angle? And the answer is yes, because that's why I picked it, right? So for which angle A is pi over 8 equal to A over 2? If you don't know what pi over 8 is half of, you can set up this equation, and you can say pi over 8 is supposed to be some angle I know, divided by 2. Really? But once it's an equation, we can solve for that angle A that we're supposed to know. We multiply both sides by the denominator. We see the 2's reduce. And over here, on the other side, on the left, 2 divided by 8, they have a common factor of 2 also. You see that 8 factors as 2 times 4, so that these 2's will also reduce. Since these 2's reduced, the only thing left on the right-hand side was A. This tells us that this well-known angle is pi over 4. In other words, pi over 8 is half of pi over 4. That's what solving this equation told us. So cosine of pi over 8 can be found by thinking of it as cosine of pi over 4 over 2. I'm taking this well-known angle and dividing it by 2. That is equal to what I started with. But the cosine half-angle formula says that this is going to be plus or minus the square root of 1 plus cosine of that better known angle A, which we found in this case was pi over 4 over 2. That is what the cosine half-angle formula tells us. Now, the way we pick plus or minus depends on what quadrant this angle is in. If this angle is in the first quadrant or the fourth quadrant, then its cosine should be positive. But if this angle is in quadrant 2 or 3, then its cosine should be negative. Which quadrant is pi over 8 in? That's right, it's in quadrant 1. So that means we're going to be the positive square root of all this business. Okay, so we picked the positive square root, and now we just have to simplify the rest of this. The reason that we picked this identity was because cosine of pi over 4 is something that we know, and we can proceed from here. 1 plus cosine of pi over 4 means 1 plus root 2 over 2. Now, of course, all that is still over 2 inside the radical. We're going to get a common denominator. So 1 is equivalent to 2 over 2. And then we can add these two guys in the numerator, which there's not really much to do because they're not like radicals. You just turn it into one fraction. The advantage of this one fraction business is that now I can simplify this compound fraction. If you didn't know that's what we were trying to do, that is what we should always think when we have a fraction within a fraction. Simplify the compound fraction. One way is to get a common denominator for all the terms on the top and the bottom. And once we have that, we can take this and multiply the numerator by the reciprocal of the denominator instead of dividing. Instead of dividing by 2, we're going to multiply by the reciprocal. 1 over 2. And that gives us the square root of 2 plus radical 2 over 4. So this is the exact value of cosine of pi over 8. Ta-da! So here's a very similar one. Find the exact value of cosine of 5 pi over 8. So I want to think of this as half of a better known angle. Again, we say this is equal to something over 2, and we solve for that something. We multiply both sides by 2 again, and these reduce again, and 2 over 8 reduced just like last time, and 2 times 5 times pi over 2 times what makes 8? 2 times 4. Just like last time, and those are going to go again, which leaves us with 5 pi over 8 is exactly half of 5 pi over 4. So we want to think of this as the cosine of half of 5 pi over 4, because that's something that we can do more easily. So we take this as our A in the cosine half angle formula, and we're going to get plus or minus the square root of 1 plus cosine of A. A in this case was our better known angle, 5 pi over 4. And that's all over 2 inside the radical. Now how do we choose plus or minus? Plus or minus is determined by the quadrant of this angle. Not the quadrant of this angle, the quadrant of this angle. 5 pi over 8. Cosine of 5 pi over 8 should be either positive or negative depending on what quadrant 5 pi over 8 is in, right? So that's how we pick, right? Great. Now, what quadrant is 5 pi over 8 in? If you don't have a lot of practice figuring out which inequality sign to put between these fractions, what you're going to do is get a common denominator. So 2 and 8 have a least common denominator of 8. I need to multiply this by 4 over 4 to get that common denominator. 4 pi over 8 is the same as pi over 2. Cool. So which of these three signs should I put in between? 5 pi over 8 is greater than pi over 2. Is it a lot greater than or a little bit greater than? Well, it's only 1 pi over 8 more. It's actually just a little bit greater than. But in case you're worried, you can show that pi, which is equivalent to 8 pi over 8, is bigger than 5 pi over 8. Now, if 5 pi over 8 is between pi and pi over 2, that places it solidly in quadrant 2. So if this is in quadrant 2, is cosine going to be positive or negative? I hope you said negative. Cosine is negative in the second quadrant. That is why we should choose the negative radical this time. Proceeding to simplify the inside of the radical. You know that this is the opposite of the square root of 1 plus cosine of 5 pi over 4. What is cosine of 5 pi over 4? What quadrant is 5 pi over 4 in? That's going to control the sign of this term. 5 pi over 4 is in the third quadrant. So you're going to have negative radical 2 over 2. And then the rest of this works very similarly to the last problem. Get a common denominator, and instead of dividing the numerator by 2, you multiply by its reciprocal. So you get a common denominator, combine the two terms, and then instead of dividing by 2, we multiply by the reciprocal, 1/2. And then we multiply these guys, top times top over bottom times bottom. And then if we want to, we can actually take the square root of the top and the bottom separately. There's nothing to do about the top, but the denominator does have a nice square root. And so you can take the square root of 4. Notice that the square root no longer goes all the way down to the bottom, and that the fraction bar now extends out past the radical symbol, right? Signifying that this is part of the numerator only. And yeah, you could go ahead and do that here too, back in our last example. That way they look more the same. Let's go ahead and tackle our next example. Evaluate sine of 7 pi over 12. So again, the first question is, what angle is this supposed to be half of? If I'm supposed to say, use a sine half angle identity, then I need to know sine of 7 pi over 12 is the sine of what divided by 2? What do I divide by 2 to get 7 pi over 12? And like before, if you have a hard time thinking of this, set up an equation. This is going to be only slightly different from the last time. These 2's, 2 in the top and 2 in the bottom, reduce. Here, 2 times 7 times pi over 12. 12 can factor, and 2 is a factor of 12. 2 times 6. So these 2's reduce, leaving us with a is 7 pi over 6. That is, 7 pi over 12 is half of 7 pi over 6. Look at that denominator. We know that angle way better than 7 pi over 12. Now go back and look at the first slide, well, the second slide with the identities on it, and see what we're supposed to get next. This is what the identity says, right? Okay. I brought it up here myself. So what am I supposed to write next? Try to use this identity and see what you get. What should go here? Pause me and I'll wait a second. Okay, so have you waited a second? Have you tried it? Awesome. I'm so proud of you. Now you'll notice that the only thing that changes from problem to problem is the a, the angle a. So we're going to write equals plus or minus the square root of 1 minus cosine of something over 2. That something is supposed to be the same here as here. So whatever angle you're dividing by 2 on this side has got to be the same angle you're plugging into cosine on this side. Here, 7 pi over 6 divided by 2. So this has to be cosine of 7 pi over 6. Now to figure out whether this is plus or minus, you ask yourself, what quadrant is 7 pi over 12 in? Think about it. Alright, now if you said that 7 pi over 12 was just a little bit bigger than 6 pi over 12, aka pi over 2, and that therefore sine pi over 12 was in the second quadrant, you are right. Next question. Is sine positive or negative in the second quadrant? Sine is positive in the second quadrant. So what we need to do now is evaluate the rest of this, simplify the numerator. What is cosine of 7 pi over 6? We have to ask this quadrant question all over again. Now it's not about our overall answer, it's about this part of it. Is 7 pi over 6 in first, second, third, or fourth quadrant? It's in the third quadrant. 7 pi over 6 is in the third quadrant, so cosine is negative, which means that 1 minus cosine becomes 1 minus a negative number. Cosine of 7 pi over 6. Root 2 over 2, root 3 over 2, or 1 over 2. If you said root 3 over 2, you are the winner. Hooray! And this becomes 1 plus. And the last steps are similar to the last steps we've done a minute ago. Get a common denominator, add the terms in the numerator, simplify the compound fraction by, instead of dividing by 2, multiplying by the reciprocal of 2, multiplying the two fractions, and then taking the square root of the bottom. This is our answer. Now that's all the examples of this kind that we're going to do here. In the future, we'll show you how to do half-angle identity problems where not the angle is known, like in this case it was 7 pi over 12. It's not one of our faves, but it is known, right? I gave it to you. We're going to do examples where I give you the value of sine A and ask for the value of sine A over 2. So I never tell you what A is in those examples. And in a different other one, we're going to do tangent half-angle identities. But for right now, if you want to go home and take your word of the day and pack it up, here's your word of the day, Quasitosaurus, the extraordinary lizard. But if you want to stick around, we're going to explain why sine of 7 pi over 12 is equal to sine of 7 pi over 12. So if you don't want to do this, we'll catch you next time. But for those of you who might remember when you did this using the sum angle identity, we got something different than when we did this just now. Pi over 4 plus pi over 3 ends up being the same as 7 pi over 12, right? So using the sum angle identity, you would get sine of pi over 4 cosine of pi over 3 plus sine of pi over 3 times cosine of, and there's no way I was going to fit that. So here we go, in a reasonable location with room for it. Sine of pi over 4, cosine of pi over 3, sine of pi over 3, and cosine of pi over 4. And when I simplify, remember that the product of radicals, root 3 times root 2, is equal to the radical of the product, radical 3 times 2, radical 6. And of course, don't forget to multiply the denominators as well as the numerators. 2 times 2 is 4. They ended up having a common denominator, so we got this. This is what happened when we used the sum and difference angle identities. We got radical 2 plus radical 6 over 4. Now, why is this equal to what we got earlier when we used the half angle formula, which was radical 2 plus radical 3 inside the radical, right? Crazy nonsense. Why are these equal? We're going to show that these are equal by showing that their squares are equal. Because if these guys have the same sign, if they're both positive, or if they're both negative, and they are positive and positive, if they have the same sign and their squares are equal, then they should also be equal themselves. So we're going to square the one on the left, and we're going to square the one on the right, and we're going to show that their squares are equal. So what do I get when I square the one on the left? Well, you'll notice that this is a fraction, and when you square a fraction, you can square the top and the bottom separately. Cool. Except that when you square the top, you notice that it has two terms. So we'll get back to that in a minute. Now the denominator squared, that's just 4 squared, that's easy. But the numerator squared, it's a binomial squared, which means that you should remember squared means times itself, so that you remember to FOIL. First times first, outside times outside, inside times inside, and last times last. First times first is going to give us root 2 times root 2, 2. Outside times outside gives us root 2 times root 6. Now, if I have the square root of a times the square root of b, this product of square roots is equal to the square root of a product. So the root 2 times root 6 is just the same as the radical of 2 times 6, radical 12. So this is 2 plus radical 12. Inside times inside, root 6 plus root 2, root 6 times root 2. It's just root 12 again. And then root 6 times root 6, last times last. These guys. Root 6 times itself is 6. Now we combine radicals. Which ones are like radicals? These two, and these two that don't have any radicals are also like radicals. 2 plus 6. And root 12 plus root 12. It's like saying, what's banana plus banana? It's 2 of them. 2 root 12s. Now before we can simplify any further, we have to simplify radical 12. We're going to use the same principle we used to do it the first time, but we're going to do it backwards. So we're going to say, are there any perfect square factors of 12? Things that have nice square roots. Factors of 12. 1, 2, 3, 4, 6, 12. 4 is a perfect square. This is 4 times 3. 4 times 3 equals 12. So the square root of 12 is the same as the square root of 4 times the square root of 3. And the square root of 4 is a nice number. This gives us 8 plus 2 times the square root of 4 times the square root of 3. Or 8 plus 4 radical 3. And of course that denominator has been hanging out there the whole time, just waiting for us to get back to it. And now we're ready. Now we're ready to say that 8 is ugly, I should draw a new one. There's an 8 you can understand. In order to finish this, we need to factor out the greatest common factor from top to bottom. What factor do the two terms in the top have in common? They both have a 4. 4 times what equals 8? 4 times what equals 4 root 3? If you said root 3, you win. Is 4 a factor of the denominator? You bet. That's kind of how we got 16, right? By multiplying 4 by itself. So these cancel. Now that I've got factors, I can reduce factors from top to bottom. I can only reduce factors from top to bottom. Notice that the numerator is written as a product, so that these factors will reduce. Finally, after squaring the left-hand side many steps later, we get this. Let's square the right-hand side. When I square the right-hand side, I'm going to square the top and the bottom separately, right? Now the square of the numerator is a square root times itself. And when you do that, you get what was inside. So the numerator, when squared, becomes this. The denominator, when squared, becomes 2 squared. That was way faster, and it turned out that they were the same thing. This is equal to this. So these guys have the same sign, their squares are the same, they are the same. I hope you stayed tuned for this algebra review. So that's really all we have for this video. Join us next time for the previously mentioned forthcoming other videos on half-angle identities. And this has been a Badger Bear production.